So once we have confined ourselves to the case of linear oscillation, then we can apply the Newton's second law to write force equal to mass times acceleration, so the double derivative of the displacement, and that's equal to minus kx. We can bring both of them to the same side, plus kx equal to 0, and then divide everything by m, so we get x double dot plus k divided by m times x equal to 0. It's customary to redefine this constant, which is, by the way, is a characteristic of the system only, because k is a characteristic of the system, or to be specific, characteristic of the spring, and m is a characteristic of the mass you hang on the spring, or you attach to the spring, and this is defined as omega naught squared, where omega naught is called the angular frequency. So finally, it takes the form x double dot plus omega naught squared times x equal to 0. And this is the differential equation that governs a class of phenomenon which is called the simple harmonic oscillation. So it's the differential equation that governs that class of phenomena. And this differential equation is important for many reasons. One of the things we can readily understand by looking at it is the fact that this differential equation makes the phenomenon of oscillation very accessible by letting us use an analytic form of the solution. So this is exactly solvable. I'll show you two different ways of solving it. The first one is by some algebraic manipulation and then by integration at 2 stages, but it's not very difficult. So discussing that solution may enlighten us, but if you have seen this solution before, then you can skip this part. So in order to solve this differential equation, what we need to do is to multiply this equation by x dot. That means the first derivative of the position with respect to time. So we have x dot times x double dot plus omega naught squared x times x dot equal to 0. We also multiply the equation by 2, so I'm rather going to write 2 here than there, and there's a reason. And both of these terms look awfully like the differentiation of a square term. If we have x squared, and if you differentiate it with respect to time, you're gonna have 2x then x dot. And if you differentiate x dot squared with respect to time, you're going to have 2x dot x double dot. So if we integrate both of these terms, we are left with the equation x dot squared plus omega naught squared x squared equal to some constant k. Sorry, I'm gonna call this one c. So this equation, the integration of this equation leads us to x dot squared plus omega naught x squared equal to constant c. Now if we apply the boundary condition, then it's possible to find out this value for c as well. So what is that boundary condition? So we'll utilize the fact that when x reaches its maximum value a, so this is x max, then the velocity x dot goes to 0. So what do? We impose the fact that 0 squared plus omega naught squared a squared equal to c, and so therefore we have c equal to omega naught squared a squared. We replace the value of this constant into our equation, and then we get x dot squared plus omega naught squared x squared equal to omega naught squared a squared. After a bit of algebraic manipulation, we can rewrite this as x dot, which is dx dt, which is also, according to this equation, becomes square root of omega naught squared a squared minus x squared, and then this is equal to omega naught square root a squared minus x squared. In order to integrate this, let me rewrite this in the integral form. So dx divided by square root of a squared minus x squared is equal to omega naught times dt, and if we integrate this, omega naught is a constant that stays out of the integration. The left hand side is gives us sine inverse, or the arcsine function, whose argument is x divided by a, and on the right hand side we get omega naught t plus omega naught times a constant, let's call it c prime, and this, the whole thing is a constant which we call delta. So finally the solution stands out to be x equal to a sine omega naught t plus delta, which is, by the way, the complete solution of the differential equation governing simple harmonic motion. Notice there are two constants. This constant is called amplitude of the oscillation, and this constant is called the phase angle of the oscillation. So the solution is a sinusoidal solution. There are two integral constants involving the solution because we differentiated twice in order to get to the solution.